So in this video we will look at the basic layout of a microscope and specifically the two main ways of illuminating the sample and collecting the signal to make the image. We've seen before that in any microscope design we can distinguish the source with the illumination part, which brings the illumination beam onto the sample, and the collection or image formation part, which collects signal from the sample and brings it to an eye or a camera to make the image. Each of these parts may consist of numerous lenses and other optics elements, but we will skip that for now and only look at the illumination beam at the sample. The first way of illuminating the sample is to project the beam to illuminate an area on the sample. This area is then also the part of the sample that will be contained in a single image. Due to the illumination, a signal will be generated throughout the illuminated area, and this signal will be collected by the collection or image formation part of the microscope and then brought to the detector, for instance, a camera. The image formation part of the microscope may magnify the sample area onto the camera, or optical components may be in the image formation part, for instance, to filter part of the signal or to convert phase changes into intensity changes. For now, that does not matter that much. The important thing to realize is that in this wide field mode, an area is illuminated at once, all signal from that area is collected, and the image is formed all pixels at once over a certain time. This is the integration time. I want to make a small note on the signal. Based on the illumination, some signal will be generated in the sample. The signal can be scattering of the illumination, transmission or reflection, or a local phase change in the transmitted beam. In the example you see here, it can be a scattering. Here, of course, only that part of the signal that is emitted or scattered into the collection angle of the image formation part of the microscope will contribute to information in the image. Any signal generated under angles outside the collection cone will not contribute. An important aspect of wide field illumination is that the illumination is homogeneous over the illuminated area. Intensity changes in the illumination over the image area will also be present in the image and might falsely be interpreted as signal differences. So, the illumination part of the microscope needs to take the light, in our case electrons, from the source and create a homogeneous illumination pattern on the sample. Typically, this criterion may limit the observable image area. Next, we need to realize that the image formation part of the microscope typically magnifies the area onto the camera in order to see fine details. Thus, the image resolution is to a large part determined by the optics in the image formation part of the microscope. Besides wide field microscopy, there's another approach. Instead of illuminating an area on the sample at once, we may also take the beam from the source and manipulate it such that it only illuminates a teeny tiny spot on the sample. We may then collect all the signal generated in a spot on the sample, for instance scattering, reflection or transmission, and use the intensity of that signal as a value for one pixel in the image. Now we only have one pixel value, so to build the image we then need to move the illumination spot to a new position, record the signal intensity from that position, and so form a new pixel. Then we repeat this for many different spots to record all pixels in the image. In our case, where we illuminate with electrons, we call this approach scanning electron microscopy, or SEM. Typically in SEM we record the signal in the upper half space above the sample. However, we can also detect in transmission. In this case we talk about scanning transmission electron microscopy, or STEM. To illustrate the recording of an image with SEM, you here see an animation. While the beam is scanning over the sample, intensity is assigned to each of the pixels and the image is gradually built. When all pixels have been scanned, we have a single image. Now it is important to realize that we need to stay a specific time on each pixel. This is the time needed to collect sufficient signal from that position. This time we call the dwell time or pixel dwell time. The total time that is now needed to record a single image is determined by the number of pixels in the image times the pixel dwell time.